Okay, so in this talk, I will touch two subjects. The first one, I will tell you about the birth of string theory, and then the second one, the low energy effective Lagrangian of QCD. And then at the end of my talk, I will talk about also my collaboration with Vadim Knizhnik. So I was getting my degree in Rome in working, and my advisor was Bruno Tuschek, the person that in Frascati near Rome constructed the first storage ring. And he gave me to compute E plus E minus in E plus E minus, sorry, E plus E minus, E plus E minus plus 2 gamma, because at that time they were thinking to use it in the monitor for the storage ring. And he gave me a paper of 2 pages by 2 Russians from Novosibirsk. And I could reproduce immediately using block Nordsik the limit in which the frequency of the two photons are small. And then I start to do the calculation in general, and it took me 1 year before I finished. And after that, while all the group in Frascati was working on radiative correction, so to the new machine that was under construction, I decided I was attracted more by S-matrix theory. And then I start to work on S-matrix theory. And so people, after the successful formulation of QED in the 40s, they were trying to apply quantum field theory also to the strong interaction. But there were 2 problems. One was the fact that there was a large number of hadrons, and the second was that the pion-nucleon coupling constant was big, so you cannot do perturbation theory. And also, you have to write a Lagrangian where you put all the hadrons. It was not very convenient. And so, under the influence of the Berkeley School, the trend on physical quantity as Lagrangian and try to construct directly observable as the X matrix. And that was done by imposing the property that the S matrix was supposed to satisfy. And this property were analyticity, crossing symmetry, unitarity, and Regge behavior. And the idea was there was no precise way how to use them to construct the S matrix, but the word that was used was bootstrap. So use the bootstrap and get out the S matrix. Now the 2 centers, the most important center that were working on S matrix theory was one in Berkeley and the one in Cambridge. And actually they produced 2 books that they have the same title. One by Jeff Chu and the other one by Eden, Lansoff, Olive, and Polkigor. Now, there was a lot of work on this S matrix, how to construct the S matrix. I think that the most important result that came out from the S matrix theory was the Veneziano model. Veneziano wrote the scattering amplitude for the elastic scattering of 2 scalar as a beta function here with linearly rising Regge trajectory and as a function of S and T, which are the 2 Mandelstam parameters. The amplitude has an infinite number of poles for alpha Sn equal an integer, and each of the pole corresponds to resonance. Now, from the residue of the pole, you can read the spin of the particle exchange, and it turns out that at the level n, you have a particle from spin 0 to spin n. The model contains infinite number of resonance with 0 width, And at high energy, one gets Regge behavior given by this formula. And actually, this formula was obtained by a group of people working on finite attenuation rule. And the group of people was Ademollo, Rubinstein, Veneziano, and Virasoro. And they were saturating finite attenuation rule. And at the end of their, they wrote a number of papers. In the last paper, they arrived to this Regge behavior. And then Veneziano thought, what is an amplitude which has this Regge behavior? And he came out with a beta function that actually has this Regge behavior. Now, the construction of this amplitude was, the people got very enthusiastic about this result. It was very explicit result that you get from S-matrix theory. And in few months, the amplitude was generalized to the endpoint amplitude, which is given by this formula. And the integrand of this formula was invariant under this projective transformation. And that means that you can fix three of the variable, which are called Koba-Nielsen variable, because in this form, the amplitude was formulated by Koba-Nielsen in 1969. And then you fix, it's convenient to fix Z1 to infinity, Z2 to 1, and Zn to 0. And the amplitude becomes this. And the alpha 0 is the intercept or Regge trajectory, which is connected to the mass of the external particle by this formula. Now, this amplitude was fallen from the sky. And if you have a Lagrangian, you construct the scattering amplitude. Here, you got a scattering amplitude, and the question was, what does it mean? Where does it come from? And so this was a difficult question. A simple question was, what is the spectrum particle that are contained in this endpoint amplitude, and what is their interaction? Now, so the key way to compute the spectrum was to first rewrite the amplitude in terms of an infinite number of harmonic oscillator and a position and momentum operator satisfying this commutation relation. And now I write here in D dimension, but you should remember that D came out much later. This was supposed to be an amplitude for hadrons, and so the dimension was 4. Now, Fubini Veneziano introduced this field, and they could write the amplitude in this way, where this is the vertex operator of the external particle. And if you take the limit of this to z going to 0, you get the state of the external particle. To z to infinity, you get the state in the bra. And this is the state operator correspondence that was later found in conformal theories. So I should stress that all this formalism was derived just by trying to rewrite the endpoint amplitude. But little by little, one discovered that this amplitude contained the two-dimensional conformal group. However, the two-dimensional conformal group at that time was not known, and the conformal theories developed later. That was developed much later by Belhavin, Polyakov, and Zhomolozny in the 80s. Remember, here we are in 69. And then those are the generators of the projective group. L0, L1, and minus 1, written in terms of the oscillator. And under the L0, L1, and minus 1, the vertex operator transforms as a conformal field. Again, at that time, we didn't know what a conformal transformation was in 2 dimensions. Then using this relation, by the way, in my transparent, there will be many formulas for those who want to understand in details what I'm saying. But in the talk, I will jump over the formula and try to give just a way to understand the logic of the development. So you use this relation and you write the amplitude in terms of vertex, propagator, until you get to a vacuum expectation. You have the propagator in the middle and 2 states at the end, which are those states here. And the propagator is given by this expression, which has pole when this quantity is 0, and this quantity is 0 when this equality appears. And so in a more simple way to understand what's happening, I wrote here, so you have a vertex here, a state here, the vertex operator, the propagator, another vertex operator, and so on. And I want to factorize the amplitude at this point here. And so I introduce 2 sets of complete state of harmonic oscillator here, and the amplitude is factorized in this way. And this is the propagator, and this has a pole when this quantity is 0. And the pole is given in this diagram. Now, the expression shows that the amplitude has pole when alpha minus p squared is an integer, and the contribution of the pole are all the oscillator that satisfy this relation for m going to 0 to n. And the number of independent states that contribute corresponds to the generacy of the state contributing to this pole. So the factorization gives, in this way, gives the contribution of all states that contribute to the pole. On the other hand, the Lorentz invariance implies that the state contributing in the residue contain also state with negative norm, because the oscillator, the 0 mode, the 0 component of the oscillator has metric which is minus, opposite to the other oscillator. On the other hand, if oscillator with negative norm are coupled, they will violate unitarity. And so the question is, how can you put together at the same time Lorentz invariance and unitarity? So to get the inspiration, we look at QED, and in QED you can look at the pole of the photon, and at the pole of the photon the amplitude factorized in 2 quantity, one having particle P1 PM and the photon, and the other part m plus 1, m plus r with the photon. And you see that the component 0, 0 corresponds to a ghost, corresponds to a state with negative norm. Now, on the other hand, you have gauge invariance. Gauge invariance tell you that Q mu, and Q nu, and nu is 0. So you go in the frame where Q is like that, and you can see that this equality allow you to cancel the component 3 and 4. And you are left only with the component along the direction x and y that corresponds to the two physical degrees of freedom of a photon, helicity +1 and helicity -1. So we learn that gauge invariance is necessary to have both manifest Lorentz invariance and absence of negative norm state of ghost. So can something like that happen in the dual resonance model? So using this relation and you are allowed, and this relation, you are allowed to put this operator start from the left of VD, putting on the right of VD, and this left invariant. And so you can move this operator all the way until you reach here. If you move once more, you get this, and that gives 0 on the state, because the state satisfies this condition. So in this case, you get a condition that it's a bit like gauge invariance before, acting on the state on the right. But one condition with an infinite number of oscillators is not sufficient, so you need additional condition. Unfortunately, Virasoro found out that for alpha 0 equal 1, there are additional conditions. But what you have to pay for this is that the lowest particle becomes a tachyon with mass alpha prime m squared equal -1. And Virasoro introduced an infinite number of oscillators in terms of an infinite number of operators in terms of the infinite number of harmonic oscillators. And he showed that this combination applied to the state on the right gets 0 for all the n positive n. And so you get an infinite number of conditions, and this gives the hope that in this way the ghost can be cancelled. Now, actually for alpha 0 equal 1, the propagator simplified to get just simple form. And at the pole alpha minus p squared equal n gets a contribution for the state satisfy this condition. So to make some example, for n equal 0, you can satisfy this only with the vacuum of this one, and that gives a state with mass square -1, which is the tachyon. At level 1, you get a massless spin 1 given by this operator. At level 2, you get this possibility, this other possibility, and they have alpha prime m squared equal 1. At level 3, you get this one, this one, this one, and then you alpha prime m squared equal 2. And the number of states increases exponentially with the mass. But because of the decoupling condition, how many of these states really contribute? And so I come to the physical condition. So the physical conditions are constructed in this way. You start from state which are off shell by m unit. On shell state are the one which are L0 minus 1 equals 0. You take state off shell by n unity, and you impose this condition on the state. So you select all the state, and you apply to this state this operator. And so you generate an infinite number of states at the on shell at the level n. But you can prove that this state are decoupled of the physical, of this state P contain a lot of vertex and propagator, because of this condition gives zero to this state P. And so this state is a state which is orthogonal to all the states. So it's not coupled to the state which has VD, VD, VD. And so we construct the states which are orthogonal to this state. So the states which are orthogonal to the state are called on-shell physical state and satisfy this condition. And that was computed in this paper in 1970. Now there is more details here that this equation do not completely define the physical subspace, because there are zero norm states that satisfy this condition that are still decoupled from the VD, VD, VD. And these states are called zero norm states. And for instance, a set of zero norm state can be computed by starting from an off-shell state by one unity, apply L, and this is a physical, it satisfies this relation. It's not physical because it's not on-shell. Satisfy L0 equals 0, but on L0 minus 1 equals 0. And then you apply to this state L minus 1, and then becomes physical, but is decoupled by the VD-VD. So you should eliminate all the state from the subspace of physical state. And you can prove that the only state which are both satisfying the physical state condition and are decoupled from VD, VD, VD can only be zero mass state. Now, the most general state at the level n equal 2 is given by this, as I mentioned before. It's a combination of these two states. Then you have to impose the condition, Ln equals 0, and you get these three states. One is spin 2, one is a spin 1, and the third is spin 0. The spin 2 is a positive state with positive norm. It contains oscillator with space index, sorry, and that is in the center of mass frame. And this is a spin 1, but you can prove that it's a zero norm state, so it decouples from the physical subspace, and this is a spin 0. And now and then if you look at the spin 0, the norm is given by this expression. So if D is bigger than 26, then this is a ghost. If D is 26, that is a zero norm state, is this state 1, and decouples on the physical spectrum. If D is less than 26, then is a physical spin 0 particle. And however, I should mention once more that that was not the analysis originally done, because the analysis was done in D equal 4, and nobody had with hadrons had in mind to think about the dimension. Now, how can you generalize this to higher level? And then we look at, people look at vertex operator for excited state. And you should consider object which are conformal field. So all the vertex operator of the excited state of the theory that we are analyzing satisfy this condition, so transform as a total derivative under the Virasoro generators. They reproduce the state when you take zeta equals 0 in this and z in infinity on the bra, and they are physical state. They satisfy also this hermiticity property, and this was done in this paper in 1970, in these two papers in 1970. And then you write a formula which is exactly like the formula for the tachyon, except now that you have a vertex operator of any excited state. And this is, there is a complete democracy between physical state as advocated by the followers of S-matrix theory in this book by Jeff Chu. And in fact, in the end of the book, he writes, perhaps a light guess about some new symmetry group with associated set of fundamental parts is destined to lead us quickly out of the wilderness. What is meant here, it meant parallel to S-matrix theory, there were people that were using current algebra. And they were trying to get the spectrum of the hadrons saturating the current algebra relation. And in particular, there was the eightfold way description of the hadrons, starting from quarks that were assumed to transform as the tree representation of SU3. Then people constructed the mesons and the baryon as irreducible representation of SU3. And so the hope was to try to find a group that included all the hadrons that you observe in nature. And that was the hope of this line of research. Now, S-matrix was orthogonal to this way of proceeding. And essentially, because people talked about quarks, but nobody found quarks in nature. There are perhaps the chief reason for the current attention on quarks. If truly elemental particle discovered, the analytic S-metric as a fundamental approach to strong interaction will lose much of its appeal. The accumulated weight of experimental evidence of a span of more 30 years, however, makes the existence of hadron aristocrat seem unlikely. Physicists, whether they like it or not, probably will have to find strong interaction theory compatible with nuclear democracy. That was written at the end of this book. Now, that did not happen for strong interaction because we know today that they are described by QCD, which is a field theory having quark and gluon as fundamental particle, and this is a non-abelian generalization QCD. And hadrons appear only as a composite of quarks and gluons. So QCD did not respect what Chu was writing. On the other hand, the previous idea based on S-matrix theory strongly contributed to the discovery of the Veneziano model and is also fashionable today to get constraint on how a consistent theory should look like. And maybe constrain so much the theory that one may end up in a unique solution. That's is the hope of many people working in this direction nowadays. But I should remind you that this direction comes directly from the S-matrix formulation in the 60s. Now, let's go back to this dual resonance model with alpha 0 equal 1. We know that we are dealing with the two-dimensional conformal algebra. In my knowledge, this is the first time that this algebra was written, and this is the first time that people understood that the two-dimensional conformal field theory was what we call the Virasoro algebra nowadays. Although you should, historically, you should remind that Virasoro never wrote this algebra. This algebra was written by Fubini and Veneziano, but without using the oscillator. They were using this formula for the Ln. And this, if you use this formula, you get only this part of the algebra. But if you use the Ln given by Virasoro, then you get the extra number. And in fact, I was at MIT in 1970, and Joe Weiss was also there. He came to my office and say, do you know that the algebra, because Fubini and Veneziano have written this part, and he said, do you know that the algebra contains also this number? And then this number, I always associate with Joe Weiss, who unfortunately died when I was visitor at CERN, because he liked to go to the mountains, and he died in the Mont Blanc. Now, the vertex operator associated with a massless vector state are somewhat special, and they'll play an important role in the proof of the no-ghost theorem. And this is the vertex operator. And by the way, if there are questions, just interrupt me. If there are questions now, just ask. Otherwise, we end at the end.
I was actually wondering, Professor Di Vecchia, I was wondering if you could say something about your interpretation of the dual models at the time, especially your interpretation of the dimensionality, the world sheet, and ghost states.
Well, all these words that you mentioned were not known when the dual model was formulated. And all these words were not known until until the point in which people proved that this dual model for alpha 0 equal 1 was connected to string. But until the end of 1972, D-dimension came before of 1972, but people didn't take care very much about, that was a paper by Lovelace. And I remember that when the paper arrived, that was probably in the fall 1970 or the beginning 1971, Fubini got the paper and he said, yeah, Lovelace is getting mad. So to show that at that time, D was 4. There was no wall sheet of the string. There was only a theory which included an infinite number of particles, all treated democratically. And those particles, there was a two-dimensional conformal theory behind this construction, but people didn't know why that. So that there were people that like Orgelbeck Nielsen, Nambu, and Susskind, that when they saw an infinite number of oscillators, they start to mention that there was a string. However, the argument they brought during these 3 years, more or less, they were not convincing enough to prove that there was a string theory. They were all heuristical argument, and I will come to this later on, that and people were not convinced. So people kept working in the model, trying to derive its property without knowing that there was a string theory. I hope I answer your question.
Yes, thank you.
And so the next step was to use the vertex operator of the photon to construct this quantity here that contains I goes from 1 to d minus 2. D minus 2 are the direction orthogonal to k, the momentum of the photon. And then you have to do an integral here, but there is a log in the Q. And so you have to impose that this condition, that axion state, which is such that this is n. And then this operator is a total derivative. Sorry, since under the ln transform as a total derivative, this commutator is 0. And they satisfy the algebra of the harmonic oscillator. Now here there is a proof. I'm going directly to the result, which is this. So this construction constructs an infinite set of harmonic oscillator that cover the direction from 1 to d minus 2. Remember that the other oscillator cover from 1 to d. So you can construct an orthogonal set of infinite state, physical state, and the question is this infinite set complete? Now, if you go back to the level n equal 2, you can use those DDF operator, and those, so the index I goes from 1 to d minus 2, so you can count, this is symmetric tensor, so you get d minus 2 times d minus 1 divided by 2 state, and from this you get d minus 2. So this is the number of state that you get. And this is the equal to the number of component of the spin 2 state at this level. So this state is the only physical state if d equal 26. However, we were doing calculation in 4. And doing the calculation at this level, we realized that there was also a spin 0. It was not decoupled in 4 dimensions. And we were very disappointed. And Fubini say that it's useless to write a paper. They are not complete. But then, fortunately, Fubini went to Tel Aviv, where there was a conference of dual models. And people got very excited to listen that there was an infinite number of physical states with positive nodes that being constructed. And so when Fubini came back, say, okay, let's write a review paper and send to Annals of Physics. And the paper came out in Annals of Physics. And but then it turned out that for d equal 26, those states are complete. And I learned from that when I was at CERN, and Charles Thorne was at CERN, was in 1972, And then he came to my office and he said, do you know, Paolo, that your states are complete in 26 dimensions? And then I look at the formula that I have in equal 4, I put 26, and I realized that he was correct. And then it turns out that, and those people did the analysis, that that in 26 dimensions they are complete. So that means that all the physical states are positive null state. There is no ghost in the dual resonance model. People also show that for D less than 26, there are no ghosts. And those states are called Brouwer state, and they already needed at n equal 2, at the level n equal 2, and the spin 0 is the first Brouwer state. Now, as I told you before, in the end of 70 or the beginning of 71, Lovelace came out with 26. So historically, I mean, people thought that the amplitude, the endpoint amplitude that I was discussing before was only the tree level of a theory which included also loops. And so people start to compute loop. And so the Veneziano model and the extension to endpoint amplitude satisfy all the axioms of S-metric theory except unitarity. In fact, in unitarity in a model with only resonance impose that the total width of resonance should be equal to the sum of all the partial width. And in a theory, ghost-free theory, all the partial width are positive definite, and so also the total width. On the other hand, in the amplitude dual resonance model, you had partial width because the particle decayed, but the total width was 0. So that was violating unitarity. So immediately after the discovery of the Veneziano model, people start to compute first one loop, and then then a multi-loop. Because also in field theory, loop diagrams are important to implement unitarity at higher loop. And then in the one loop case, there were two kind of diagram. One was the planar diagram, and the other was the non-planar diagram. And they had all the correct branch point required by unitarity, but the non-planar loop had branch cuts violating unitarity. And so remember, the circle without anything in the middle is the disk. If you put two disks, two circles, the quantity inside here that you see is like an open string propagating in a loop here. But again, open string was not known at that time. But the loop was computed, nevertheless. And in the planar, you have all the external particles on one circle. In the non-planar, you have external particles both in both circles. And in this loop, Lovelace found out that there was a branch cut violating unitarity. But if you put equal 26, the branch cut becomes a series of poles that corresponds to closed string. And in fact, you could have imagined already there was a string theory, because you can take this circle and pull out of the screen. And you see that you get a cylinder, and the cylinder contains a closed string going from one circle to the other circle. And that is exchange of a closed string. So that was obvious a posteriori but was not obvious while we were working on the model. And so you get the state of the open string, like on those rigid trajectory, the state that Lovell extract from the non-planar loop lie on this rigid trajectory. But at that time, practically nobody took seriously the Lovelock's observation. And but this has been the first evidence that of the critical dimension. Now, I must remind you that in parallel with the Veneziano model and its extension to an external particle, there was also the Shapiro-Virasoro model. Virasoro wrote this amplitude for 4-point amplitude, and Shapiro generalized to n particle, and that turned out later on to be amplitude for closed string. So let's move towards string theory. So up to now, there was no evidence, and although there were only those people mentioning string theory, the Lagrangian or relativistic string was written by Namu Gotha in 1970. But you should remember that the FADEP, of course, was introduced just in those years, and BRST quantization appeared in 74. Here we are 1970. And in those years, people were starting to understand how to quantize theory, having redundant degrees of freedom as gauge theory and also string theory. Another problem in the discussion was that the Virasoro algebra that appears in the string model that they were constructing by these people is a classification algebra, as in conformal field theory nowadays. But in the dual models was a gauge algebra. It was not classifying particles, but was eliminating particle, was imposing condition to have gauge invariance, essentially. So in the point particle, you write this action, having the mass which is proportional to the length of the path of the particle. In string theory, you have proportional to the area spanned the string, and this went under the name of Nambu-Goto. We had to wait until the end of 72 to have the proof that the spectrum of the dual resonance model and that extracted from the string Lagrangian quantized in the Lycon gauge was the same as that extracted from the dual resonance model. And that was a fundamental paper by Goddard, Gostan, Rebbe, and Thor. They made a gauge. You know, in string theory, tau and sigma can be any parameter. There is a complete invariance. You can reparameterize. They have no physical meaning, but you can decide, and that they chose a gauge to say that this tau is X plus, is this light cone combination of the string coordinates. And then using the Ln condition, the classical level, you can compute also X minus and X in terms of the transfer state. They also construct the Loda generator only in terms of this transfer state and show that they satisfy the Lorentz algebra only if d equal 26. And the quantization of open string reproduced the spectrum of the dual resonance model, while that of the closed string reproduced that of the Shapiro-Virasoro model. Then in this very physical and interesting paper, Brink and Nielsen computed the 0-point energy, so the trajectory of the string, again by this sum, that can be written in this way, and that gives 1 for d equal 26 if you use this. This formula was used by Gliozzi in 76. Brink and Nielsen, they use a lot of physical consideration because the quantity diverges, as you see here. But they extracted the infinite part, and they managed from the infinite part to extract the physical finite part, and this is what gives 1. The paper is not easy to read, but is very physical. Immediately after, it was shown that the 3-point coupling from the 3 strings in these 2 papers reproduce the coupling of 3 arbitrary DDF papers were computed in this paper. The endpoint amplitude was also computed using 2 methods, one having interaction with an external field in this paper, or using path integral in the light-cone gauge by Mandelstam. It's interesting that the only physical state that can interact with a string are only states that are also physical state, excited state of a string. And this tends to give you that there is not, that does not exist anything outside of string theory. Also, scattering amplitude involving open and closed string were computed in this paper. And before leaving string theory, let's have to mention that one loop and multi-loop were also computed in 69. And there were several papers. I'm not mentioning all these papers. One of the persons that strongly contributed was Lovelace. And there is a physics report by Alessandrini Amati, Lebellac, and Olive. It's interesting because in this paper, they were finding functions that were well defined on Riemann surfaces. But at that time, it was not obvious why there was a Riemann surface, because it was not obvious that there was a string theory. And so the N loop green function was computed, appear already in these papers, and the only thing that was not possible to compute was the measure of integration, because that was possible only the discovery of BRST invariance, and that appeared only later on in 87, where the complete n-tachyon multi-loop amplitude was computed in terms of the H loop here. H is the genus. This is the H loop Green's function, and given here in terms of the prime form, the abelian differential and the period matrix. And this is the integration measure. The formula derived at that time was in the Schottky parametrization of the Riemann surface and in terms of the multiplier and fixed point of the Schottky parametrization. And this is the parameterization around the puncture that were chosen according to Lovelace. Now, that's the end of string theory. And I continue to work on string theory until 76. But between 72 or 73 and 76, and nobody cared anymore about string theory. I taught with several other colleagues, mostly from Italy, but also with Lars Brink from Sweden, and also a paper with John Schwartz from the States. And we continue to work until in 1976, together with Lars Brink and Paul Howe, we wrote the Lagrangian that corresponds to the Goto-Nambu for the superstring. I remember that we were at the Niels Bohr Institute in Copenhagen, and we were working in one room for a week. And we wrote a transformation, and then we proved that the variation of the Lagrangian gave a total derivative. And then after we finished the paper, I told to Lars and Paul, don't talk me anymore about string theory, otherwise I don't get a job. And so I was profiting from the fact that Sasha Polyakov was visiting the Niels Bohr Institute in 76 for 3 months, and he was giving lecture on instantons and non-abelian gauge theory, also monopoles and all the stuff. And so I start to learn the stuff. And since I know supersymmetry, I start to apply this stuff to the supersymmetric theory that were not known to the people that develop instead instanton and other things. And in fact, when Sasha Polyakov came to Copenhagen in 76, he told me that his dream would have been to work on string theory. But in Russia, there was nobody working on string theory. And so he managed to get into string theory only in 82 with his famous paper. But it was interesting, at that time, Polyakov came to Copenhagen and he wanted to work on string theory. And I told him that I had to forget string theory in order to get a job. And then I want to show you at the end of his stay here in Copenhagen, Sasha, we organized a conference on this new development. Oh, sorry, I should have. Let me first conclude, and then I'll show the picture, okay? So the conclusion that we can make nowadays, it's that open string include gauge theory, while closed string include gravity. And if you start from open string, you get closed string at one loop. And if you start from closed string, you get open string at non-perturbative level from the deep brain. In conclusion, you cannot have a gauge theory without having gravity and vice versa. And this is what we observe in nature. In D equal 10, one gets few string theory that depends only on the string length, this parameter that has very similar form to the Planck length, of course with C and H. But string theory is not in contradiction with field theory, but is an extension of field theory. By performing zero-slope limit, one gets gauge theory and gravity, as shown in this paper. And if you do that zero-slope limit in many different ways, you get almost all the consistent field theories. And these appear in those papers, but there are many other papers. So string theory has the characteristic of being a theory of everything. But the problem, and it's more or less unique in 10 dimensions, but if you go to 4 dimensions, then you have many, you have to compactify 6, you have many theory, And you cannot use string theory to predict what you want to observe at accelerator energy. But that is also true in field theory. Field theory cannot predict the standard model. The standard model has been constructed to reproduce the data. And so what one has to do, one has to search for compactification that contain the standard model, classify them, check if they are stable, stabilize the moduli space, and write the four-dimensional effective action and see if fit with the experiment. But this is a not easy task. So I go back to the point before, and I show this picture. This picture is taken from the meeting in '76, and you see that the situation was very different than nowadays, where people are very much specialized. Here you have people like Maiani here, David Gross, Sasha Polyakov, Simancic, Fubini, and Martinelli, working in phenomenology, and Bengt Nagel, he was chairman of the Nobel Committee, and other people. So essentially this Cortal Altes in Marseille, and Dada and Sciuto here. And at that time, particle physics was pretty much unified. I mean, this new development with instant, with monopole, brought attention to everybody. And that was a situation which was pretty much different than nowadays. So that ends up my discussion of string theory. I don't know if there are other questions.
Was the distinction between world sheet supersymmetry and space-time supersymmetry known at the time?
Well, it was clear that the string theory contained n=1 world sheet supersymmetry. And then with the work of Gliozzi, Oliver, Scherk, with the GSO projection, they showed that there was also space-time supersymmetry. So space-state supersymmetry. So these are two different supersymmetry. I should have reminded you that supersymmetry means space-time supersymmetry, if you want, was also born out of string theory. And in fact, if you go back in history, Zumino gave a series of talks at a conference in Capri, where he discussed the Navier-Schwartz-Ramond model that has, the model that I've been describing is the dual resonance model, which has only the Virasoro algebra, but the Navier-Schwartz-Ramond model had n=1 world sheet supersymmetry. And Zumino was studying this model, and he was translating this model as a two-dimensional field theory. And I remember that we had lunch together at CERN, and he said, but I mean, this model is two-dimension in this world sheet, but why can't we extend supersymmetry to four-dimension and construct supersymmetric theories? And then, I had lunch with him and Julius Vess a few months later, and at lunch they say, okay, we found a model involving only scalars. That was probably 1973, that is supersymmetric in four dimensions. And that was the Vess-Zumino model. And that was the starting of supersymmetry. Now, the fact that supersymmetry was discovered in '76, also in string theory, I mean, nobody cared. You know, people have developed field theories, supersymmetric field theory, and there was an whole community developing supersymmetric field theory that was different from the community of string theory. The only person that was in common was Joel Scherk, that he wanted to work in string theory, but because of the development, everybody was working field theory, so he was also working in field theory, and he wrote a lot of interesting papers. But although eventually space-time supersymmetry was found also in the string theory, one had to wait until 84 because people start to take care of this. Okay, so here I come to, so in Copenhagen, after having worked with, on string theory until 76, I start to work on instanton, but then I the fortune that Tarda and Lüscher were visitor in Copenhagen, and we start to work on the CPN model. Now that was a good model to fill the gap of what I could not follow, because between 73 and 76, everybody doing hadron physics was working on QCD, and I was working instead on string theory. So this model had many properties in common with almost all properties in common QCD, and so we were studying this model. So let me quickly remind QCD as this Lagrangian contains quark and gluons. If you neglect, there are the quarks have two indices, one is color, one is flavor. There is a mass matrix in flavor space. If you neglect the mass, you have a conformal invariant theory because both G and theta are dimensionless quantity. When you do the perturbative theory at one loop, there is dimensional transmutation. So at the quantum level, the coupling constant is replaced by a physical energy scale, which is called lambda QCD, and you have a running coupling constant. And then you have a beta function with negative, and so you have asymptotic freedom at short distance, but the running coupling constant becomes infinity at large distance. And you have to use non-perturbative method. One is lattice gauge theory, the other one over an expansion. But QCD is a matrix theory, the Lagrangian expansion cannot be performed explicitly. It's just a sum over all the planar diagrams. And so you cannot have an explicit formula. It turns out that quark and gluon are confined. You observe only hadrons, which are baryons and mesons. The massless theory contains, it's chiral invariant. It's invariant under two transformation. And at the quantum theory, the vector current is conserved, and the axial vector current has an anomaly. And the anomaly is given by the topological charge density that in the large n, since you keep G square n fixed, goes to 0. So at large n, the anomaly disappears. So you would like to write an effective Lagrangian for the composite field. And this is not, you can guess the Lagrangian in QCD, but you cannot construct the Lagrangian. But in the CPN model, you can actually perform the large N expansion, and starting from the fundamental Lagrangian, which contains quark and gluon, you can explicitly construct the large N Lagrangian that describes the hadrons. And so that is the reason why we start to study this model. So this model is a model containing n scalar, complex scalar particle with this constraint. And if you conveniently scaling to keep f fixed in the large n, you write Lagrangian in this way. Actually, this Lagrangian was written by Eichener, and this Lagrangian was analyzed in two papers together with Dada and Luscher, and in a paper by Ed Witten in '78. So you had to add also fermions this way, and they have two indices, one color and one flavor. There is also topological charge density, and if you neglect the mass, it's also conformal invariant. The conformal invariant is broken by loop diagram. It's asymptotically free. And there is U1 NF close to U1 NF symmetry, which is broken by the anomaly. So it's exactly a model like QCD. And now, if you introduce auxiliary field, you can write a Lagrangian which is quadratic in the fundamental field. And so you had to compute this path integral containing this Lagrangian is quadratic in the fundamental field. And these are the external source to generate Green's function. And then you can compute the path integral, and you get an effective Lagrangian containing only the composite field. And the effective Lagrangian is this Lagrangian contain trace log of this and trace log of this. And now what you have to do, you have to expand the effective Lagrangian. There is a n, n, and f for large n, n, and f. The leading term is the vacuum energy that is a number. And then the next two terms are of the order square root of n and square root of nf, that the coefficient of this term are proportional to the alpha field. And this coefficient in the large n is a saddle point, should be eliminated. And the fact that you require elimination, you get this saddle point equation that is obtained by this quantity that you regularize with Pauli-Villards. So you add this term. Then you introduce the denormalization, the denormalized constant in this way, and you get the denormalized constant in terms of this m squared that is correspondent of lambda QCD. So m is the renormalization invariant physical scale replacing f. For the fermionic sector, you need to introduce a vacuum expectation value for the phi 0. And this is the singlet, the flavor singlet field. And that implies that you get spontaneous breaking of axial symmetry, precisely like in QCD. And essentially, you can go through the same formulas and define the renormalized coupling. And then you can compute the beta function. You see that it's negative, both beta function and so the asymptotic free as in QCD. And then you look at the term which has order n. Sorry, of order n to the 0 and nf to the 0, containing the quadratic term of the composite field. And these are those terms written. So you start to discover that you have the pseudo-scalar, which were described. These terms are massless in the limit of 0 mass, and and so they are the Goldson boson of the spanning broken axial symmetry. The scalar field instead have a mass even in the massless limit. And then there is this coupling to the topological charge density, and it can be better written in this form. So, and so this form, again, these are the pseudo-scalar, these are the scalar, and there are this coupling. These three are the most important coupling. And this Lagrangian contains f pi, that in 2 dimensions is dimensionless. This is the pi decay constant, and what is called the topological susceptibility, which is this. And then from this Lagrangian, you can compute the Green's function, which are given by this expression. And you see that the singlet gets a mass which is not equal to the non-singlet. And the mass is given by this term. And this equation is what today is known as the Witten-Veneziano relation. Now, these formula were derived in 1979. Historically, Witten knew the CPN model. So he knew that this relation was satisfied in a CPN model. And then he wrote a paper where he brings some argument how this formula can be satisfied also in QCD, in the Lagrangian expansion. And then he got this formula where now chi is the topological susceptibility in QCD, and f pi is the f pi in hadron physics. And then when I went to CERN in the end of 1978, I found that Veneziano was using the anomalous word identity to try to get this formula. And then I sat down and I constructed this 2-point amplitude, and that shows that they satisfy the anomalous word identity, and that shows that how to reproduce the Witten-Veneziano relation. Now, I more or less too. It's important to mention that here that this the singlet gets a contribution where here you have the 2-point amplitude of the topological charge, and that is a 2-point in a theory without quarks, and this is the 2-point amplitude that Witten in his paper proved to be non-zero at 0 momentum. Now, you should remember that topological charge density is a total derivative, and for that reason disappears in any calculation that you do in perturbative theory, in perturbation theory. But and so that means that in perturbation theory, you cannot have any dependence of the theta parameter in the observable, and therefore at the perturbative level, this quantity is 0. But at large n, large N expansion is non-perturbative, and in large N you can get a non-zero value for this matrix element, for Q, for the two-point function of Q. So I come to the effective, I'm a bit out of time, I guess, but okay, let me continue. Then I stop when I arrive to 5:30. So in QCD, the axial anomaly, the axial symmetry spontaneous is broken, and the pseudo-scalar meson are the Goldstone boson. And so you can try to write a Lagrangian which has the same symmetry as in QCD. And this is the nonlinear sigma model is the Lagrangian that people were writing. And this Lagrangian has the same symmetry at the classical level as the QCD. Symmetry in flavor space, that means the flavor symmetry, so this UNF cross UNF symmetry. But the field of the pseudo-scalar meson for n equal 3 are those fields, the pion, the kaon, the eta, and the eta prime, and they have this mass. The U1 problem was a problem because with only having mass quark different from 0, you never can make the meson to have this splitting. And so the one problem was how can you be able to solve this problem, to have a mass of the pseudo-scalar to have this splitting also in QCD. So here I show that they have the same symmetry, the same UNF plus UNF symmetry, but I can go over. And then on the other hand, the Lagrangian I wrote before, which are the first two lines, as all the UNF symmetry, but we know that in QCD there is one anomaly, and so we have to add the term that reproduce this anomaly. And this term is this one that was extracted by Riva from the CPN model and turns out to be also good for QCD. So, so we add this term, but once we add Q, why not to add also another Q square or a function of Q and U? And now it turns out that if you add other terms, they are non-leading in large N. These are all the terms that you can add at large N. And if you make a transformation by the anomaly given by this term, you get the Lagrangian is not invariant, but transformed as the anomaly requires. And so this Lagrangian was written in a series of papers. And actually, when we were discussing this problem, I was at CERN together with Veneziano. Also Ed Witten was at CERN, and Sidney Coleman was at CERN, and Rod Kruger was at CERN. We were discussing a lot, and Witten had to go to Cargès to give lecture, and so we left each other to try to write this Lagrangian, and with the idea to write a paper together. Then we kept working, and we wrote this Lagrangian, and we wrote a paper together with Veneziano, and we sent the paper to Witten. At the time, there was no archive. The telephone was not used, was very expensive. We sent the paper to Witten with also his name on the paper. And then we were waiting probably 3, 4, 5 months. I don't remember exactly. And after this period, we received another paper by Witten with all the name on it. And we look at the paper, and it took a while before we could recognize the two papers, that was the same that we did in our paper. And so we wrote back and forth. In the end, we decided to write two different papers that that have more or less the same content. And that's why I wrote two different papers here. And the analysis that I will do in the following are essentially contained in these two papers. So, okay, so at large n, there is no other term containing Q and U, and so you can integrate the Q here, because Q appears without any derivative on it, and you get this Lagrangian. Now, now you have the theta parameter here, and then you have to adjust the vacuum expectation value of U. So you have to, since U dagger is proportional to unit matrix, and the mass matrix is diagonal, you can take the vacuum expectation value to be this. And so in the previous Lagrangian, you can insert this in terms of this Q. So the term without phi, capital Phi, gives you a potential, which is this. And the phi are determined by solving this minimization equation. And so, and the phi are determined as a function of theta, the parameter A that appears in the effective Lagrangian, and the quark mass, mu I. And then you insert, so there is this potential, and then the rest of the Lagrangian can be written in this form, where the singlet came out with a mass given by this parameter A. And now the quark mass depends on the parameter phi I in this equation. And then you get, because of the theta parameter, terms which are CP violating terms given by this term. And then you can start to look at the spectrum of mass, looking at the quadratic part. So I guess the idea is clear. You, let's see, you have to solve this equation. You solve this equation for psi. You plug in this Lagrangian, and then you get everything that depends on theta, mu I, the parameters appear in the quark mass matrix, and A, which appears here, and also in the solution of the minimization equation. Now, at the quadratic level, you have this expression, and so you separate the field living in the Cartan subalgebra here, and the rest. The rest have a very simple mass metric, the mass. For the field living in the Cartan subalgebra, you have this matrix that you have to extract, and this matrix is the inverse of this matrix where A appears and B is have 1 in any entries. And so the physical mass are given by the determinant of A. So there are the eigenvalues of this matrix that can be written also in this way. And if you take the mass to 0, you see that you get n-1 massless state and one state which has this mass. And this parameter A, it goes like 1 over n. And so you see that this mass is proportional to nf or n. So this appears for large n exactly like the anomaly. Now, to see that the problem, U1 problem is resolved, you look at the spectrum, and that was Veneziano did in his paper. In the case where mu1 and mu2 are much less than mu3, and you get this formula in terms of this A and the mass of the meson, and also the mixing angle. Now, you can, if you put eta prime mass with a plus and then eta with a minus, so the sum of the two, you can use the mass, the sum of these two mass to determine A, and you get this. And then you put back A into the equation and you get the mass of the eta and eta prime. That's what Veneziano did. And you get this value to be compared with the physical value, which are very close. But then you need to have a solution of this. One problem, you need to compute this correlator. And so from the A that you have computed from the formula I mentioned before, and F pi that is about 95 MeV, you get this value for the topological charge density, 1/4. That the number that I found from lattice calculation gives this number, which is pretty good agreement with the large n. So in this way, you could say that the one problem has been solved, but has been solved because you don't only take into account the fact that the quarks have different mass, but also because an extra contribution coming from the U1 anomaly. So this opened the way to study theta dependence of physical observable, and that are zero, that they don't depend on theta in perturbation theory. And in the case of two flavor, you have to solve, and for A much big, to solve this equation. So that gives this parameter in terms of the mu parameter, the quark mass. The mu are essentially proportional to the quark mass. And then you can insert in the potential, you get this, and for equal mass, you get this. And you can see both are periodic in theta. And actually, it turns out that any observable is periodic in theta due to the periodicity of the minimization equation. You can solve more general equation, which are those for small epsilon, and you get this, and you can compute this parameter, which gives you the violation of your CP violation. And so you can see that this term is zero if theta is zero, or if one of the quark mass is zero. Is if the two, if the mass are not the same, then it's zero also at theta equal pi. But if the quark mass are the same, then you have a CP violation of theta equal pi. And then from this violation, the term which has CP violation, you can extract the decay of eta in 2 pi that is violates CP, and you can extract the value of theta, which is less than t minus 3. On the other hand, well, is you can add baryons to the effective Lagrangian, and you can compute a a pion, the pion nuclear coupling constant from the Goldberg-Trima relation. But with theta, you can also have a term which violates CP. Using them, you can compute the electric dipole moment of the neutron. And we computed in this paper, we get this number, and that tells theta must be much less than 10 to the minus 9. And that, so if experiments show that theta is very small, and so it's very natural to find a mechanism to force theta to be 0. And the Pei-Quinn found such a mechanism, and this mechanism essentially consists in our effective Lagrangian to add the term, kinetic term, for these extra degrees of freedom, and adding an anomaly term, which is because of this broken new one Pei-Quinn symmetry. And this is a Lagrangian that was written in this paper in 2014. And now both U, N, and Lagrangian transform under U1 group in this way. But then you can choose the parameter in such a way that you have a subgroup which is conserved, is broken only by the mass term. And the breaking of this anomaly-free subgroup implies a new pseudo-Goldstone, which is called the Pei-Quinn-Weinberg-Wilczek axion. And so, in fact, proceeding as before, the potential is modified by the fact that you have also this extra field. You have to write the minimization condition, but they are satisfied for all phi equals 0 and for theta equal pi. And that means that there is no dependence of theta, and the CP is conserved. And then you can use the previous Lagrangian to compute the axion mass, which is given by this expression, which is what Wilczek and Weinberg and Wilczek computed, and which has the same expression as the singlet mass, but here there is a topological susceptibility of QCD, not that of Young-Mills. And here there is a ratio between the two. You can see that the one for QCD goes to 0 when work mass is 0. But the recent result gives this value for Q, the key for chi QCD, and you get, this is the prediction for the axion mass as appear in this recent paper. Also restricting to the field of the Cartan subalgebra, you can compute the axion potential, and essentially was the potential that we derived in the paper with Veneziano, where here there was the theta, where substitute theta with this with the axion field. And that has been stressed later on in, I mean, of course, we were not aware. Our paper was 1980, and Pei-Quinn is later on. That was stressed in this paper, and the analysis was repeated in this other paper. So let me come to the last part, where I want to remind you about Vadim Knizhnik. Now, Wess and Zumino constructed the Lagrangian, incorporated all the terms coming from the anomalies word identities, not only the one that I discussed before, but also those coming from the non-abelian anomalies. So when you couple Young-Mills to non-abelian field living in flavor space, you get all non-abelian anomaly that they were discussed in this paper by West and Zumino. And they actually integrated the anomalous word identities and construct some of the terms. But then later on, Witten in 83 construct all the term. And so this Lagrangian is called Wesen-Zumino-Witten. And this Lagrangian has the property of reproducing all the anomaly, the anomalous word identity. Now, in 2 dimensions, the Wesen-Zumino-Witten Lagrangian was formulated in these 2 papers. The first one was formulated in this way, and this way contains also the external gauge field. But if you put a gauge field to 0, and if you use this U, you can see that this Lagrangian is reproduced by this, which was constructed by Wigman and Polyakov, and which is called the Wesen-Zumino-Witten Lagrangian in 2 dimensions. Now, the first paper that Vadim wrote was on the 2-dimensional theories invariant under Virasoro and Kazmudi algebra. That's a paper that by now is a fundamental paper. And the paper contains also a study of the Wesen-Zumino-Witten model. Now, at the time of Soviet Union, NORDITA used to organize meeting. NORDITA is a meeting, it's an institute created by the 5 Nordic countries, Denmark, Sweden, Norway, Finland, and Iceland. And it was located in Copenhagen at that time. And NORDITA used to organize meetings where physicists from the West met Soviet physicists, either in Moscow or in Copenhagen. And I went to, and the 2 people responsible for that was Alan Luther, who was professor at NORDITA in solid state fever, and Kalatnikov, who was the director of the Landau Institute in Moscow. And the Landau Institute was close to the base where the astronauts were doing exercise. And so when we had this meeting, we were not allowed to go to Landau Institute. We had the meeting in Kapitsa Institute in Moscow. And so usually we had meeting for about 2 weeks, discussing physics. The Soviet people discussed what they found, and we discussed what was found in the West. And I went to one of these meetings in 84, and if I remember correctly, Vadim came to the airport to pick me up. I came late to this meeting, as far as I remember. And then I gave a seminar on the construction of the supersymmetric Wesen-Zumino-Witten model. After the seminar, Vadim came to me and he said that he had tried, but did not succeed to construct. And he thought that what I was telling in the seminar was not completely true. But then he said, okay, let me check it again. And then in the last day of the meeting, there was a party at the house in Moscow, in the apartment of Tsomoloshnikov. And Vadim came with a few pages showing in his formulas that he agreed with the supersymmetric Wesen-Zumino model that I presented in the seminar. Most of the people at the party, everybody, they were in a very high spirit due to the large amount of alcohol available, except us discussing what was written in these notes. And many people came around telling us to stop, to discuss physics and enjoy. But for us, it was the last chance to discuss about this, because the next day I was leaving, going back to Copenhagen. And at the end of the discussion, we discussed what to do. And Vadim told me, take the notes and do whatever you want with it. And so I replied, okay, I write a draft and I'll send to you. And then you can add whatever you want to the draft. And then he said it was not possible. And we could do whatever we want with our draft. So I went back to Copenhagen, where it took a while to understand his notes. And we look at the paper that he wrote with Somoložnikov. And finally, we managed to understand, and we wrote a paper in which we wrote our way of finding the supersymmetric Wess-Zumino axion. And then in section 5, we discuss in detail what was in those notes. I was very happy to collaborate with him, breaking the rule that Soviet physicists only collaborate with Soviet physicists, and people from the West only collaborate with people from the West. That was practically, I guess, one of the, maybe the only paper that appeared at that time were both. And I was very happy because for me, collaboration has been always much more important than competition. I want to conclude this mentioning another paper by Vadim, where he wrote together with Belavin, Morozov, and Perelomov, he wrote the partition function of the bosonic string at 2 and 3 loop in terms of these modular forms that can be written in terms of theta functions. Now, I mentioned you before, and that's the reason why I mentioned that we have an expression for the multi-loop endpoint function with tachyons. However, if we neglect the part with the tachyon, we can extract the partition function. And Kai Roland, that was a student here in Copenhagen, he went through the calculation and he showed that the measure, so if you translate the metrics, the period metrics in terms of the Schottky parameterization, and you write also this theta function in terms of Schottky parameterization, and then you expand for small moduli, then you reproduce exactly the measure that I was mentioning a few slides before. And so, and with that, I end and mentioning that unfortunately Vadim is not with us anymore. And he has essentially the same destiny as Joel Scherk, who made a lot of very important contribution, and also he left us when he was only maybe 34. Okay, thank you very much, and I'm happy to answer any question.
Professor Di Vecchia, thank you very much. Are there any questions? I actually wanted to ask about, so when you moved away from string theory in 1976, did you follow the developments such as, GSA projection and, covariant quantization methods? And of course, there's, Polyakhov's famous work. And I was wondering if you had, actively followed any of these developments at the time.
What happened was that in 76, I follow all the development until 76. So corresponding to the GSO projection. Then I worked on instanton, and in 81, I think, if I'm not wrong. Yeah, in 81, because after I left CERN in 79, I got a job in Berlin, and then I moved to Wuppertal. And so in 81, I was in Wuppertal, but I was still in contact with people in Copenhagen. And so I wrote, I think, several papers. First on the non-abelian bosonization, but then also on the new development essentially coming from Dan Friedan. And I forgot now exactly the years, but I remember that we were studying some paper of Dan, and then in 82, Lars Brink went to a meeting in Moscow, and he brought back a paper by Polyakov on the 26, the anomaly. And then I was visiting Copenhagen often in the summer, working with Jens Lund Petersen and Bergfinn Durus. And we were studying in details the paper by Polyakov. And so I must say that I already got a job in Germany, and I didn't have to worry about the future. And so I start to study again the new development. And so we wrote some paper on the unitary minimal models. I think Dan Friedan and other collaborators got in n equals 0, probably also in n equals 1, but then we work out n equals 2 minimal models, which were unitary. And in that period, probably around 82, 83, I was getting, again, inside all these things. And I remember that when people in Wuppertal start to know that I was working on these things, they say it was good that you were not working at that time, otherwise you will never got a job.
I see. Thank you very much.
Yeah. I don't know if there are other questions.
Yeah, if there aren't any other questions, we'll end the talk here.
Okay, but then thank you very much.